Hey there folks, my name is Matt, and on behalf of Hackaday, I wanted to reach out to you to share with you an interview I got to do with a very interesting gentleman, a guy by the name of Mr. Ivan Godard. And I'm not sure if you remember, but a few weeks back we had done a piece on the mill CPU. Well, Mr. Godard is part of the founding team over at Out of the Box Computing, and they're the guys that are responsible for the mill CPU architecture. So go ahead and have a listen.
So tell me a little bit about the team. How many people are actually working on this?
We have been a bootstrap, self-funded startup from the beginning. We have an extremely legally novel organizational structure. It is called a company of incorporators, and all corporations go through this stage. Let's say that you and I decide we're going to open a pizza parlor. And in order to do this, we have to put a deposit on the lease and a deposit to the power company. But the corporation doesn't exist yet. So what we do is we make a contractual agreement between us that we'll do this, and then when the corporation papers come out, we'll split the company in such and such a way. That intermediate stage, when the thing is in the process of being organized but has not yet actually happened, is called a company of incorporators, and legally it goes back to the Middle Ages. And there's a case law for it, because we may have gotten all these deposits done and you get hit by a bus, and suddenly now what happens? Well, the case law exists to establish this. Normally this process exists for a half an hour in the lawyer's office in the process of closing. We have been using this form for 10 years. It has one very major advantage. We can re-divvy up. As people contribute more work, they get a larger share of the enterprise. But because there actually is no corporation, they're not actually getting re-shares. What we're doing is we're rewriting the terms of the contract, which is the company of incorporators. And as a result, because that's merely a contract, this is not a taxable event. They haven't received anything. So unlike a situation in which you work, you get stock, we have to put a value on the stock, in which the finance people normally cheat, but you don't actually get stock, you get an option that's worthless. And frequently is worthless, but that's a different question. We follow this other model. We have no bank account. We have no premises. We are a distributed company, people scattered all over everywhere. We make use of conference rooms belonging to our co-location. When we need a conference room, you're sitting in it. And it's been very much like a open source software project in terms of its organizational structure and the headaches. Any person who's ever attempted to do a big open source software project will tell you it's like herding cats. And yes, that has been our case. And we've been doing it for 10 years. Headcount is varied. There are people who have day jobs. I've been full-time from the beginning. There are other full-timers. There have been people who've been full-time, then they'll go get a job, and then they come back and be full-time again. Anybody who's been involved in open source knows how this works. Socially, we're an open source project. Legally and commercially, we're a business.
So how close are you? I mean, how close are you to actually going out and producing silicon? Maybe you can't tell me that. I can't tell you correctly. I can tell you what our best projections are. Mm-hmm. You never know where you're going to get when you're a startup. With luck, optimal funding, and no great disasters, solving the existing tool chain problems and getting an FPGA is a year to 18 months. From that, in order to go to a product, again, assuming that everything works right, is a year, maybe another 18 months beyond that. That gives us something to sell. So we're looking perhaps 2 to 3 years to saleable silicon. But there's many a slip to a cup in the lip. Okay. So tell me, from a design tool standpoint, what does it take to actually create the mill architecture?
Well, we realized we were going to be a family fairly early on. I mentioned this. And if you're going to be a family, this means you're going to be producing a lot of different chips. And we have enough experience amongst us to know that attempting to do chips on an individual million monkey basis the way it is usually done is absolutely hopeless for a startup. A startup might be able to do custom layout for one chip, but not for 10 across the family. Consequently, we elected to take a completely different tack. The mill is based on a specification and dynamically generated facility. Each individual mill core, take a Gold, for example, which is a moderately high-end family member. The specification of that lists the components which go in it. It's got so many adders, it's got so many multipliers, the cache is this big, the belt, which is covered in one of our videos, is so big. And this is just a bunch of specifications. These can be mixed and matched, configured in a different way. At the low end, a tin is got a quarter of the facilities of a Gold, but it's built the same way. The specification is 2 or 3 pages of C++ code compiled, and then in the context out of that we build the sim for that chip. The same occurs for the instruction set. The instructions are not defined. No one has ever done manual layout of bits in an instruction. We simply say, well, here are all the operations and here are all the flavors that they can be varied with, and here are the functional units that the specification said is going to go in it, and these are the operations this functional unit is able to do, and we just collect all of the operations that across all those functional units that can be done and build mechanically in software an optimal bit level instruction set that nobody ever looks at, because we are mechanically from that building an assembler, a compiler back end, a sim, and most interestingly, driving the Verilog generators that build the hardware.
Interesting.
This has been working for several years. One of our upcoming talks will be a live demo in which I'll ask the audience to specify me a new operation. I will add it and set the thing to working, and in 20 minutes we'll have a processor running in simulation that contains that operation.
Wow. So it's all parameterized?
Completely. Top to bottom.
Wow. That's extraordinary. I mean, just that technology is a product, right? I mean,
yeah.
There's a product in that capacity.
Well, other vendors have attempted to do a mix and match sort of architecture, but always at a much larger granularity and never at the instruction set level.
Sure.
And it works. It works real well. And that presentation is probably, wild guess it'll be December, maybe early January when we'll be doing that. We have to organize the location and timing of these, and
sure.
So I can't give you a definite timeline.
Sure. Wow, but that sounds extraordinary. I mean, that's it. So through this process, you guys have effectively designed the tools
ourselves
to design the device.
Yes, you're one step up. It's meta specification, and from that producing the software. But then in turn, that has to well, it produces the Verilog, and the hardware team are expecting that they will be able to extend it. They're working on it all the time, of course. They'll be able to extend it also to do a fair amount of the place and route work as well, which will at this point still be manual, but they keep adding to the capabilities of it. It will never be, the result will never be as good as an enormously well done hand layout
of the chip. But you could say the same thing on the software side. Compiler output is never going to be as good as assembly language handwritten perfect code if you can afford to do it. But if what you want is time and acceptable rather than perfect, then you don't write an assembly language. And the same occurs on the hardware side.